Welcome to Lecture 8. This week we're going to finish talking about double and triple integrals. We'll start by using polar coordinates to do double integrals. I introduced polar coordinates in the last lecture. And then we'll move on to triple integrals. First, triple integrals in rectangular coordinates, and then triple integrals in three-dimensional polar coordinates, in either cylindrical polar coordinates or spherical polar coordinates. And then we will finish today's lesson by doing substitutions in multiple integrals. Let me just remind you what we were doing in the last lesson. If we wanted to define a double integral over some region R, then we needed to divide the region R up into little rectangles using vertical and horizontal lines. And then we were just counting the rectangles which were completely inside the region. On top of each one of these rectangles, we drew a column. We added up the volume of the columns, and that was our double integral. We're going to be doing the same idea now, but instead of using horizontal and vertical lines, we're going to be using rays and circles. So let's suppose we have some rays starting at the origin, and let's suppose we have some circles about the origin. We're going to use this to cut our region R up into lots of little pieces. And we're only interested in the pieces which are completely contained inside R. On each one of these pieces, we're going to draw a column. We're going to calculate the volumes of each column, add them together, and that will be our double integral. But before we can do that, what is the area of one of these pieces? We have a little bit of angle, capital delta theta k, and we have a little bit of radius, capital delta rk. But what is the area of this piece? After we've found that, we can set up our Riemann sum. We can take the limit as the size of the partition. The norm of the partition goes to 0, and that will give us our double integral. But what is capital delta AK, and therefore what is dA? Now, let me remind you that our little bit of area, delta AK, is delta x, delta y when we use Cartesian coordinates. But when we do polar coordinates, it's not delta r, delta theta. Why? Because look at these two pieces that I've shaded in dark orange. They have the same angle because they're between the same two rays. So delta theta j is the same as delta theta k. And I've deliberately drawn it so that delta rj is the same as delta rk. But you can see from the picture that the area of these two pieces are not the same. So what is the area of something like this? What's the area of a circle? The area of a circle is pi r squared. I want to think of that as a half 2 pi r squared. Area of half a circle, of a semicircle, is a half pi r squared, where pi is the angle in the middle. If we're using radians, then the area of a sector like this is a half theta r squared. Okay, next idea. I want to calculate the area of this orange piece. Let's say that the center of this piece has the coordinates rk theta k, so then the distance from the center of this piece to the origin is rk. That means this green distance is going to be rk minus delta r over 2, and this blue distance is going to be rk plus delta r over 2. Now, we could have this blue sector. We know the area of this blue sector. we could think about this green sector. Again, we could calculate the area of this green sector. And then I'm saying the area of the orange piece that we want is the blue sector minus the green sector. We can do these. We know how to calculate the area of a sector. So it's going to be half delta theta, open bracket rk plus delta r over 2, close bracket squared, and then minus the area of the green piece. The same formula, but with minus instead of plus in the middle. Let's play with this. I'm going to multiply out the brackets, and then I'm going to cancel some terms. Half delta theta, and then rk squared plus 2rk delta r over 2 plus delta r squared over 4 minus rk squared plus 2rk delta r over 2 minus delta r squared over 4. What can we cancel here? There's an rk squared and a minus rk squared. Cancel those out. I also have a delta r squared over 4 and a minus delta r squared over 4. So we'll cancel these out as well. That leaves us with 4rk delta r over 2. Or 2rk delta r in the bracket. The 2 will cancel with the half. And we're left with rk delta r delta theta. That is the area of this orange piece. That justifies this theorem. When we're doing double integrals, a little bit of area, delta capital A. If we use Cartesian coordinates, that's dx dy. But if we use polar coordinates, this is r dr d theta. For the rest of this section, we're going to be using this r dr d theta. Okay, look at this region R. I want to find limits of integration for this R using polar coordinates. So my first question is, what are the smallest and biggest possible values of the angle theta here? The point with the smallest theta is going to be this point just here, where the angle is 45 degrees or pi over 4. And the points with the biggest possible theta are going to be on the y-axis, where the angle is 90 degrees or pi over 2. So in this region R, theta must be between pi over 4 and pi over 2. Next question is, what are the smallest and biggest possible values of small r here? Well, the smallest r is when we go into the region. Go into the region when y is equal to square root of 2. That's the same as saying r sine theta is equal to the square root of 2, or r is root 2 cosec theta. So the smallest possible r is going to be root 2 cosec theta. And what is the biggest possible value of r here along this line? When this ray leaves the region R, on the circle R equal to 2. So the biggest possible R is going to be R equal to 2. If we integrated over this region, then we would have theta between pi over 4 and pi over 2, small r between root 2 cosec theta and 2. So a double integral of some function f dA over this region R is the integral from pi over 4 to pi over 2, integral of root 2 cosec theta to 2, function f, and then instead of dA, when we're doing polar coordinates, we need this extra r. It's r dr d theta. Let's do another one. Find the limits of integration for integrating a function f over the region R, which lies inside the cardioid. R is equal to 1 plus cos theta, and outside the circle R is equal to 1. So in other words, we're in the section which is shaded blue in the picture at the top. First, let's talk about theta. What's the smallest theta here? Smallest theta is going to be minus pi over 2, and the biggest theta here is going to be theta equal to 2. Think of all of the rays starting at the origin which intersect our blue section. These rays have angles between minus pi over 2 and pi over 2. So the first part of our answer is going to be integral from minus pi over 2 to pi over 2. Next, we need to talk about small r. So just pick one ray starting at the origin and ask, when does it enter the blue region and when does it exit the blue region? It enters on the circle r equal to 1, so the smallest possible value of r is going to be 1, and it leaves on the cardioid r is equal to 1 plus cos theta. That's the biggest possible value of r. So our integral is going to be between 1 and 1 plus cos theta. And before I go on, let me just remind you, when we do an integral in polar coordinates, we have r dr d theta. We could use this to calculate the area of a closed bounded region. And the idea is, just as we did in the last lesson, we're going to integrate the function 1 over r. So we're going to be doing the double integral over r of r dr d theta. Another example from the book. Find the area which is enclosed by the lemniscate r squared is equal to 4 cos 2 theta. Now, in this picture, we're asked for all of the area which is inside this shape. So if I color it in, we're asked to calculate all of this blue area. But by symmetry, what we can do is we can just calculate the area of a quarter of this region, and then we can multiply it by 4 to get the answer that we want. So that's why it's 4 multiplied by an integral. Let's set up the integral. What's the smallest angle in the part which is currently shaded blue? The smallest angle is 0. What's the biggest angle? The biggest angle is pi over 4. So we're going to be doing integral from 0 to pi over 4. Look at a ray. For example, this ray which is drawn in red on the picture. Where does this enter? It enters when r is equal to 0, and it leaves when r is the square root of 4 cos 2 theta. So we're going to be doing the integral between 0 and the square root of 4 cos 2 theta. And never forget, we always have to have an extra r here. It's r dr d theta. I'll leave the rest of this example for you to read in the book, or if you rewatch this lesson. Just check that you're happy that the answer is 4. We had some formulae in the last lesson to change Cartesian coordinates into polar coordinates. X is r cos theta, y is r sine theta, x squared plus y squared is r squared, and tan theta is y over x. I'm going to add one more formula to this box. The other formula that we need for integrals is that dx dy is the same as r dr d theta. So, for example, calculate the double integral over the region R of e to the power x squared plus y squared dy dx, where R is the region shown in blue in this picture. So that's the region underneath y is equal to the square root of 1 minus x squared. Now, this is a difficult Cartesian integral. But if we change this into a polar integral, then we can change it into an easy integral. So let's do that. We're filled partly in already. Instead of dy dx, we want r dr d theta. What about the function? E to the power x squared plus y squared. That's just the same as e to the power r squared. We need to find the limits of integration. First, theta. What's the smallest theta in this region? The smallest theta is going to be theta is equal to 0. That's just this part which I'm drawing in orange. And what is the biggest possible theta in this region? Just here in green. The biggest possible theta is when theta is equal to pi. So on our first limits of integration are 0 and pi. What about r? What values can r take in this semicircle? The smallest r is going to be 0, and the biggest r is going to be 1, because we're on a circle, r equal to 1. So our second limits of integration are going to be 0 and 1. And then all that's left to finish this question is to calculate this double integral. An antiderivative of e to the power r squared r is a half e to the power r squared. Calculate this at 0 and at 1. To get a half e minus 1. And then we integrate that between 0 and pi. It's a constant with respect to theta, so it's just pi over 2 e minus 1. Let's do another one. Calculate the integral from 0 to 1. Integral from 0 to the square root of 1 minus x squared plus y squared, dy dx. Now, note, if we try to do this as a Cartesian integral, we can do the first one, we can integrate with respect to y, but we get this complicated thing here. And this is not easy to calculate. So instead, let's change this into polar coordinates and calculate it as a polar integral. First, what is our region of integration? I have x is 0 and x is 1. I also have y is equal to 0 and y is equal to the square root of 1 minus x squared. We know that we are between these four curves. So we know that the region of integration is going to be this region shaded in blue. In polar coordinates, this is the same as theta is between 0 and pi over 2. R is between 0 and 1. Okay, let's change our Cartesian integral into a polar integral. First thing, and I know I'm repeating myself, but it's because every year we see the same mistakes in exams. dy dx is the same as r dr d theta. Don't forget you have to put an extra r in. We need to change the limits of integration. We've just done that on the previous slide. Theta is between 0 and pi over 2. R is between 0 and 1. And then the third thing that we need to change is our function. Instead of x squared plus y squared, we want r squared. And then it's an easy integral to calculate. It's just integrating r cubed. You know how to do that, so I'll just tell you the answer. I'll leave it for you to check that the answer is pi over 8. Let's take another example from the book. Find the volume of the solid region bounded above by the paraboloid z is equal to 9 minus x squared minus y squared, and below by the unit circle in the xy plane. Here's a picture. We have this, it's almost a cylinder. It's not quite a cylinder because the top is rounded like this. And we're going to be using polar coordinates to describe this. Our region of integration is going to be this circle. It's a circle of radius 1 in the xy plane. For a circle, theta can be any angle between 0 and 2 pi, and because the circle is radius 1, r can be any number between 0 and 1. Our function 9 minus x squared minus y squared we can replace by 9 minus r squared. And dA we replace by r dr d theta. I'll leave this for you to check. Check that the answer is 17 pi over 2. There's one more example in the textbook, which I'm not going to cover here. I'll leave example 6 in the textbook for you to read. Section 14.5 is about triple integrals in rectangular coordinates. In the last lecture and the start of today's lecture, we've been studying double integrals. Now we're going to look at triple integrals. Triple integral over some region D of f of x, y, and z, dv. dv is going to be our little bit of volume. And for example, we could use this to calculate the volume of a closed bounded region D in space, just by integrating the function 1. We need to talk about finding limits of integration. On the outside integral, the left integral, the way I've written it, this is going to be the x limits, and these can be only numbers. No functions here, just numbers a and b. For the second integral, we are allowed to have functions of x. And on the inside integral, we're allowed to have functions of x and y. So a similar idea to double integrals with extended. An inside integral can be functions of the variables which are outside of it, but you can't have an integral which is a function of limits of integration which are functions of the variables which are on the inside of that integral. Let's look at this region D. First thing we would be interested in, what are the possible values of x? Oh, here they are. X is going to be between A and B. Then we might ask, what are the possible values of y? So we draw a line which is parallel to the y-axis in the xy plane, and we ask, what are the biggest and smallest values of y on this line in the region R? In this case, it's g1 of x and g2 of x. And then pick a point in R and do a vertical line going upwards. Where do we enter our region D and where do we leave our region D? We enter at F1 and we leave at F2. So that's what this means. Let's do an example. Let S be the sphere of radius 5 centered at the origin, and let D be the region under the sphere, but above the plane Z is equal to 3. Set up the limits of integration over D. Okay, so the first thing to ask is, what is the shadow? What is R in the xy plane? If Z is equal to 3, put 3 into the sphere equation, x squared plus y squared plus z squared is 25. We find that we're left with x squared plus y squared is equal to 16. So that tells us that our region R is a circle of radius 4. Here it is. We need x and y limits of integration in this circle. We know how to do this. X can be between -4 and 4. And then y is going to be between minus the square root of 16 minus x squared and square root of 16 minus x squared. All that's left is the z limits of integration. This time I'm going to show you a sideways picture. Imagine that we're standing in three-dimensional space on the x. So imagine that this is a picture of you. You're standing just here, and you're looking at the region D. What are the z limits of integration? Let's draw a vertical line. We go into the region D when z is equal to 3, and we leave at the top. Because we're on a sphere, we're leaving when z is square root of 25 minus x squared minus y squared. So now we can write down our triple integral. The integral for x between -4 and 4, integral for y between minus root 16 minus x squared and root 16 minus x squared, and then integral where z is between 3 and square root of 25 minus x squared minus y squared. Let's do another example. Look at this tetrahedron. This is a tetrahedron where the vertices are at the origin at 1, 1, 0, at 0, 1, 0, and at 0, 1, 1. I want to set up the limits of integration over D using the order dz, dy, dx. Okay, so we're going to be doing this. We're going to be doing an integral with dz, dy, dx. And what I want to do is I want to start with the outside integral. I want to start with x. What are the possible values of x in this tetrahedron? X must be between 0 and 1. Next, let's look at R, so the shadow of our region, or the shadow of our region on the xy plane, or in this case, the part of our solid object which is in the xy plane. And I want to ask, what are the possible values of y inside this region? I'm going to draw my line as I usually do, and I'm looking at the part of the green line which is in capital R. It enters capital R when y is equal to x, and it leaves it when y is equal to 1. Y is between x and 1. And then thirdly, I need my z limits. So now I'm interested in a vertical line. This vertical line enters this tetrahedron when z is equal to 0, and it leaves the tetrahedron on this surface. It's through the plane passing through the origin 1, 1, 0 and 0, 1, 1. We've talked about planes. We talked about how to find the equation for a plane passing through 3 points. This plane can be written as z is equal to y minus x. So this red line leaves the tetrahedron when z is equal to y minus x. And that's what we needed. Now we can write down our triple integral at the top of the slide. This is the integral from 0 to 1, from x to 1, from 0 to y minus x of some function f dz dy dx. Let's do this question another way. Find the volume of this, oh, sorry, I'm getting ahead of myself. Find the volume of this tetrahedron by integrating the function 1 over d using the order dz dy dx. Okay, we know our limits of integration. We've just talked about these. 0 to 1, x to 1, and 0 to y minus x, and we're integrating the function 1. Here's the whole calculation. I don't want to spend time here. I'll leave this for you to check later. Find the volume of this tetrahedron by integrating the function 1 over d, but this time using the order dy dz dx. Okay, first we need a shadow, a region capital R. And this time R is going to be in the xz plane, always the last two. So let's project this tetrahedron onto the xz plane, or shine a light where y is now and look for the shadow. Here it is. We rotate this around a little bit. What are the x limits in this orange triangle? X goes between 0 and 1. What are the z limits? Between 0 and 1 minus x. And then we need to find the y limits inside the tetrahedron. Again, I'm going to rotate this a little bit. This green line enters the tetrahedron when y is equal to x plus z, and it exits the tetrahedron when y is equal to 1. So we want the integral from 0 to 1, integral from 0 to 1 minus x, integral from x plus z to 1, dy dz dx. Here's the calculation. I'll leave this for you to check. Check that the answer is 1 over 6. Find the volume of the region D, which is enclosed by the surfaces. Z is equal to x squared plus 3y squared, and Z is equal to 8 minus x squared minus y squared. Well, first of all, this is the blue surface, and this is the red one. We want the region which is enclosed by these two surfaces. So we want something which looks like this. Find the volume of this. I'm choosing to do dz, dy, dx. So I want my shadow to be in the x, y plane. Here's my shadow. I'm going to call this R. Let's look at the shadow first. Let's look at this green oval. We obtain this green shadow when the blue surface intersects the red surface. So we get this when 8 minus x squared minus y squared is the same as x squared plus 3y squared. Playing with these, we find that x squared plus 2y squared is equal to 4. So we must have the ellipse x squared plus 2y squared is equal to 4. What are the limits of integration here? First, what possible values can x take? X is between minus 2 and 2. Next, y. Y is going to be between minus square root of 4 minus x squared over 2 and square root of 4 minus x squared over 2. And then finally, what possible values can z take? That's easy, we're told in the question. We're told that z must be between x squared plus 3y squared and 8 minus x squared minus y squared. So we've got our limits of integration. We just need to calculate the volume of this object. We want the integral from minus 2 to 2, integral from minus square root of 4 minus x squared over 2 to the square root of 4 minus x squared over 2, integral from x squared plus 3y squared to 8 minus x squared minus y squared, dz, dy, dx. And I'll leave this for you to do. Check it, fill in the details. You should get, as long as I haven't made a mistake here, you should get 8 pi root 2. Average value of a function. Average value of a function capital F is 1 divided by the volume of D multiplied by the triple integral of f over d. For example, find the average value of capital F is equal to x, y, z over this cube. That's the cube where x is between 0 and 2, y is between 0 and 2, and z is equal to 0 and 2. One way to write this cube is the closed interval from 0 to 2, cross the closed interval from 0 to 2, cross the closed interval from 0 to 2. First one is where is x, second one is the possible values of y, and the third one is the possible values of z. So we have 1 over the volume of a cube multiplied by the triple integral over this cube of x, y, z, dx, dy, dz. Everything is symmetrical here, so it doesn't matter which order we do our integration. We could do dz, dy, dx here if we wanted to, it wouldn't matter. The volume of the cube is, of course, 8. So it's 1 over 8, integral from 0 to 2, integral from 0 to 2, integral from 0 to 2, x, y, z, dx, dy, dz. And this one I'm going to leave for you to finish. Check that the answer here is equal to 1, please? I'm going to take a break soon, but before the break, I want to talk about some properties of triple integrals, sum rule, constant multiple rule, etc., etc. And I just want to say they're all the same as for double integrals. There's nothing different here. So let's not waste our time. Instead, let's take a break until 2 o'clock. Okay, let's continue. There's two more topics we need to talk about. Triple integrals in polar coordinates, and finally we'll talk about substitutions. Now, we talked about polar coordinates in 2 dimensions before. X is equal to r cos theta, y is equal to r sine theta, etc. I want to extend these ideas into 3 dimensions. A point in 3-dimensional space, x, y, z, we could replace the x and the y with polar coordinates and then keep the z just as it is. So just as we were doing before, x is going to be the same as r cos theta, y is going to be r sine theta, and z is going to stay the same. Z is equal to z. These are called cylindrical coordinates in R3. The point x, y, z has cylindrical coordinates r theta z. So, for example, find cylindrical coordinates for the point with Cartesian coordinates 1, 1, 1. We use the formulae at the top. X is r cos theta, y is r sine theta, and z is equal to z. So r must be the square root of x squared plus y squared. Theta must be inverse tan of y over x, and z is equal to z. Put the numbers in, we get root 2, pi over 4, and 1. All we're doing is we're doing polar coordinates for the first 2 coordinates. We're changing x and y into r and theta, but z is just staying the same. Z is equal to z. Let's go the other way. Convert the cylindrical coordinates r theta z equal to 2 pi over 2, 2 to Cartesian coordinates. We've got our formula at the top. Oh, there's a typo here. X is r cos theta, y is r sine theta, and z is equal to z. So that's 2 cos pi over 2, 2 sine pi over 2, and 2. 0, 2, 2. Now, cylindrical coordinates are good for describing 3 things. First of all, vertical cylinders which have the axis on the z-axis, shown in the figure at the top. These are all r is equal to a constant. They're also good for horizontal planes. Z is equal to a constant. And they're good for planes which contain the z-axis. Planes which contain the z-axis are theta is equal to a constant. Now, let me remind you that when we were doing double integrals, we had a little bit of area dA. That was the same as dx dy, or in polar coordinates, it was the same as r dr d theta. Now in triple integrals, we have this little bit of volume dv, and previously we've been saying that's dx dy dz. If we use cylindrical coordinates, that's the same as r dr d theta dz. Let D be the region in the picture. That's the region which is bounded by Z equal to 0 on the bottom. It's bounded by x squared plus y minus 1 squared is equal to 1 on the sides. That's a cylinder. And it's bounded by Z is equal to x squared plus y squared on the top. Find the limits of integration in cylindrical coordinates. First, we're going to be looking at the circle R, which is in the xy plane. Here we are. And we need to change this. We need to change this into polar coordinates. So just as we did last week, I want to replace x squared plus y squared plus by r squared. And then what am I left with? I'm left with a 2r, 2y, but 2y is the same as 2r sine theta. Rearrange it, cancel one of the r's. This circle is r is equal to 2 sine theta. Okay. If we're in this circle, if we're in this the inside of a circle, what is the smallest angle? What is the biggest possible angle? The smallest angle is 0 and the biggest possible angle is pi. What is the smallest r? 0. What is the biggest r? 2 sine theta. Let's go back to the three-dimensional picture. What is the smallest z? Down the bottom when z is equal to 0. And what is the biggest possible z? On the top, x squared plus y squared. That's the same as r squared. So z must be between 0 and r squared. So our triple integral is integral from 0 to pi, integral from 0 to 2 sine theta, integral from 0 to r squared. Then there's our function. And then instead of dv, we have r dz dr d theta. Let's do another one. Calculate the triple integral over d of the function z dv, where d is the region in this picture. We're inside the cylinder x squared plus y squared is equal to 4. The bottom of this object is the xy plane. That's where z is equal to 0. And the top is the paraboloid z is equal to x squared plus y squared. Or the top is z is equal to r squared. If we're in here, theta can be any angle between 0 and 2 pi. We're in a cylinder of radius 2, so r is going to be between 0 and 2. And then z is going to be between 0 and r squared. So let's do this calculation. We're doing the integral from 0 to 2 pi, integral from 0 to 2, integral from 0 to r squared of the function z. And remember, when we're doing polar coordinates, including cylindrical coordinates, we have this extra r. So r dz dr d theta. First, integrate with respect to z. An antiderivative of z is a half z squared. And calculate this at 0 and at r squared. Next, we need to integrate the function of half r to the power 5 with respect to r. That's straightforward. We're left with 1 over 12 r to the power 6, which we need to calculate at 0 and at 2. And we're left with 16 over 3. And then we're integrating this with respect to theta between 0 and 2 pi. We end up with 32 pi over 3. There's another type of polar coordinates that we can use in 3 dimensions. We could use spherical coordinates. And the idea is this. We're going to describe the position of a point P using 3 numbers, rho, theta, and phi. Rho, which we could think of as the Greek letter R, is the distance between this point and the origin. Theta is the same as before. Theta is the angle in the xy plane between the x-axis and this ray, which I've drawn in blue. And now we have another angle. The angle phi is the angle between the z-axis and the line from the origin to P. Okay, so before we had x was r cos theta and y is r sin theta. But what is r? Look at this picture. In this triangle, this angle is also phi. So we can see that r must be rho sin phi. And z must be rho cos phi. So that tells us that x is rho sin phi cos theta, y is rho sin phi sin theta, and z is rho cos phi. Rho is the distance from the point to the origin, so rho is the square root of x squared plus y squared plus z squared. Now, when we did polar coordinates in 2 dimensions, I said r could be positive or it could be negative, it doesn't matter. This time, for rho, it does matter. Rho, we want to always be a non-negative number. Phi, we want to be between 0 and pi. 0 means pointing directly upwards. Pi means going straight downwards. Theta, doesn't matter. Theta can be any number. Convert the point root 6 pi over 4 root 2 from cylindrical to spherical coordinates. I've written the equations that we need at the top. Rho is the square root of r squared plus z squared. Theta is equal to theta. Theta doesn't change. Z is equal to rho cos phi. So we have that r is root 6 because we're starting with cylindrical coordinates. Theta is pi over 4 and z is equal to root 2. Put these into the equations and we can find that rho is 2 root 2. Theta doesn't change. Theta is still pi over 4. Phi we can find is pi over 3. Another one. Convert the point minus 1, 1, minus root 2 from Cartesian to spherical polar coordinates. Again, the equations that we need are at the top. We need to find rho, phi, and theta. Rho is easy. Rho is the square root of x squared plus y squared plus z squared. That's just equal to 2. Next, we want to calculate phi. And remember, phi should be an angle between 0 and pi. Phi is inverse cosine of z divided by rho. So we can calculate that's 3 pi over 4. And then finally, we need to find a theta. Sine theta is y over rho sine phi. So we can calculate that sine theta is 1 over root 2. Theta could be any number. It doesn't have to be between 0 and 2 pi if we don't want to. We could choose any number. Which numbers satisfy this equation? Two possible ones are pi over 4 and 3 pi over 4, but only one of these can be correct. Which one is it? Remember, x is -1 and y is 1. And I want this angle theta. Is this pi over 4 or is this 3 pi over 4? Of course, from this picture, we can see that theta must be 3 pi over 4. So an answer to this question, there's infinitely many correct answers, but one answer to this question is 3 pi over 4, 3 pi over 4. Okay, so what are spherical coordinates good for? Spherical coordinates are good for describing three things. Spheres centered at the origin, because a sphere has equation rho is equal to a constant. They're also good for describing cones, which have the vertex at the origin and the axis of the cone on the z-axis. Because cones like this are phi equal to a constant. Now actually, if we had phi equal to 90 degrees, we would have the whole of the xy plane. I haven't drawn it very well here. This should be all of the xy plane. And again, if we increase phi a little bit more, we go all of the way down to the z-axis. Phi equal to 180 degrees, or pi, is the negative z-axis. And spherical coordinates are good for describing half planes which contain the z-axis, because these are theta is equal to a constant. Why is it a half plane now, not a whole plane? It's because now we're saying that rho must be a positive number. So we're only going to get half a plane. Let's take an example from the book. Find a spherical coordinate equation for the sphere x squared plus y squared plus z minus 1 squared is equal to 1. The equations that we need are at the top. We're going to use these equations to replace x, y, and z. And then we're going to cancel where we can. Of course, cos squared plus sine squared is equal to 1, and then again, cos squared plus sine squared is equal to 1. All cancels down, and we are left with rho is equal to 2 cos phi. This is the sphere. Rho is equal to 2 cos phi. Find a spherical coordinate equation for the cone z is equal to the square root of x squared plus y squared. I'm looking at this calculation at the bottom. Start with this equation, replace z by rho cos phi. Replace x squared plus y squared by r squared, which is rho squared sine squared phi. Take the square roots. Rho is a positive number. Phi is between 0 and pi, so sine phi must be a positive number. Cancel the rows. We have cos phi is equal to sine phi, and then we know that we must have phi is equal to pi over 4. The equation for this cone is phi is equal to pi over 4. Okay, what about when we're doing integrals? Remember, a little bit of volume. dv is the same as dx, dy, dz, and is the same as r, dr, d theta, dz. When we use spherical polar coordinates, the equation that we need to remember is rho squared sine phi d rho d phi d theta. And I'm not going to prove this formula to you. This is just a formula that you need to remember for the exams. Okay, I'm writing this at the top. We're going to be using this for the next few slides. Calculate the volume of the region enclosed by the sphere. There's a typo here. It should be the sphere rho equal to 1. And the cone phi is equal to pi over 3. Okay, so first we need the limits of integration. Look at the circle at the bottom. Look at the shadow capital R. Theta must be between 0 and 2 pi. Next, what values can phi take? We're inside the cone, so we're between the z-axis and the cone. The z-axis has phi equal to 0 and the cone has phi equal to pi over 3. So phi must be between 0 and pi over 3. What about rho? Rho goes from the origin to the sphere. So rho must be between 0 and 1. Once we know those, we can calculate the volume of this region by integrating the function 1. That's triple integral over d, 1 dv. Integral from 0 to 2 pi, integral from 0 to pi over 3, integral from 0 to 1. And then instead of dv, we have rho squared sine phi, d rho, d phi, d theta. And I'm not going to spend time calculating this. I'll leave this for you to check. Check that this should be pi over 3. Now I have one for you to do. So we have a hemisphere, rho equal to 2, but inside the hemisphere we've removed the small sphere, rho is equal to cos phi. If we hadn't removed the small sphere, then it would be A. But because we have removed this little sphere from the middle, it can't be A. So which one is it? Let me give it another hint. Look at D. D says that 2 is smaller than cos phi, but cos is always between -1 and 1. We can't have that cos is bigger than 2, so it's not D. So we're going to have 50-50. Is it B or is it C? I misspoke earlier when I talked about A. I said if the sphere wasn't missing, it would be A. A is wrong, but for a different reason. A talks about phi being between 0 and pi. 0 is straight up and pi is straight down. So A would be the whole sphere. So it's not A for that reason. And it's not D because we can't have cos is bigger than 2. So far we have 4 people voting B and 4 people voting C. I can tell you that 4 of you were correct. The correct answer is C. Theta is between 0 and 2 pi because we're anywhere around the circle in the xy plane. Phi is between 0 and pi over 2. 0 is straight upwards, and pi over 2 is the xy plane. Because we've removed this little sphere from the middle, rho starts at the surface of the little sphere and it finishes at 2. So rho must be between cos phi and 2. Okay, just to finish this section, let's just recap the important equations to remember. X is r cos theta, y is r sine theta, and z is equal to z. If we're doing spherical coordinates, x is rho sine phi cos theta, y is rho sine phi sine theta, and z is equal to rho cos phi. But perhaps more importantly for us, because we're doing integration, dx, dy, dz is the same as dz r, dr, d theta, r in there somewhere. And this is the same as rho squared sine phi, d rho, d phi, d theta. That leaves us with one section to talk about. We need to talk about how to do substitutions in multiple integrals. Just recap. What do we know from single integrals? We know that if we're trying to calculate a single integral like this, we do a substitution. We write u is equal to 2x plus 3. We replace our dx by a half du, and we also change the limits of integration. Instead of integrating between 0 and 1, we have to integrate between 3 and 5. I want to do the same thing in double integrals. First, we need something called the Jacobian. The Jacobian of a coordinate transformation, x is equal to guv and y is equal to huv, is this. There's 2 ways to write this. We could either use j for Jacobian, or we can write curly d xy divided by curly d uv. I'm going to be using the second one because for me it's easier to understand or easier to remember which variables go on the top and which variables go on the bottom. This is equal to the determinant of a 2 by 2 matrix. The determinant of the partial derivative dx du, then the partial derivative dx dv, partial derivative dy du, partial derivative dy dv. If you don't know determinants yet, and we don't teach it until Mathematics 3 in this university, just remember that this is the same as dx du, dy dv, minus dx dv, dy du. So that's first one over first one. Where are we? First, we're doing dx du, and we're going to multiply that by second one over second one, multiplied by dy dv. And then we do minus, and then we swap them around. We swap the positions of u and v. For example, find the Jacobian of the polar coordinate transformation. X is equal to r cos theta and y is equal to r sine theta. So I want to calculate dx comma y over dr comma theta. So it's first over first, second over second, dx dr multiplied by dy d theta, and then minus, and then we swap the positions of the things on the bottom. Dx d theta, dy dr. So that's cos theta, r cos theta, minus r sine theta, sine theta. And because cos squared plus sine squared is equal to 1, that's just equal to r. But remember that dx dy is equal to r dr d theta. Theorem. First of all, don't worry too much about this. This is just me being careful. I'll say it anyway, but don't worry too much. Suppose that f is continuous over the region R. Let G be the pre-image of R under the transformation. X is G of U and V, Y is H of U and V, which is assumed to be 1-to-1 on the interior of G. If the functions G and H have continuous first partial derivatives within the interior of G, then. Okay, I said that, now forget about it. That's just being careful. What I'm interested in is the formula at the bottom. Let me emphasize this. The integral, the double integral over a region R of a function f of x and y dx dy is the same as the double integral over a different region G of f of g of u and v, h of u and v, multiplied by the absolute value of the Jacobian du dv. So this is how we do substitutions in multiple integrals. The dx dy we're going to be replacing by absolute value of the Jacobian of the transformation du dv. And the other thing that we need to take care of is we need to change the region of integration. So you might get questions like this. Calculate the integral from 0 to 4, integral from y over 2 to y over 2 plus 1 of 2x minus y over 2 dx dy by applying the coordinate transformation. U is 2x minus y over 2, v is equal to y over 2, and integrating over an appropriate region in the UV plane. So there's two things we need to do before we can start. We need to work out this new region of integration. That's step 1. And then step 2, we need to calculate the Jacobian of this coordinate transformation. First, I want to talk about the region of integration. what are we starting with? We're starting with y is between 0 and 4, and x is between y over 2 and y over 2 plus 1. And what does that look like? That looks like this. And we need to do our transformation. We're told that we're going to use u is equal to 2x minus y over 2, and we're told that we're going to use v is equal to y over 2. Now let's just change these, swap these around to solve for x and y. That's the same as saying that we're going to use x is equal to u plus v, and we're going to use y is equal to 2v. Okay, so there's 4 lines we need to change. In the xy plane, we have the line y equal to 0. That's the same as saying v is equal to 0. We also have this line at the top, y to 4. Y is equal to 4 is the same as saying v is equal to 2. So over here on the right-hand picture, I'm drawing v equal to 2. Next, in the xy plane, we have the line y is equal to 2x. That's the same as saying u is equal to 0. So over in the uv plane on the right, I'm drawing the line u equal to 0. And then there's one more line to do. We also need to do y is equal to 2x minus 2. That's the same as the line u equal to 1. So our new region of integration is going to be the rectangle between v is equal to 0, v is equal to 2, u is equal to 0, u is equal to 1. This is going to be our region G, our new region of integration. So that's step 1. We know that after we do our substitution, we're going to be integrating u between 0 and 1 and v between 0 and 2. The next thing we need to do is to calculate the Jacobian of this transformation. I want dxy over duv. So it's dx du, dv dy, minus dx dv dy du. 1 multiplied by 2 minus 1 multiplied by 0, or 2. And then we're ready to go. Now we can do the integration. This is what we want. We want to calculate this integral. And I've put everything that we need at the top. 2x minus y over 2 is the same as u. So we're just going to be writing u there. We're going to be integrating u between 0 and 1 and v between 0 and 2. And we also need to put in the Jacobian. The Jacobian we found is just 2. So we're putting in the absolute value of 2. So all we're doing here is integral from 0 to 2, integral from 0 to 1, 2u du dv. And that's easy, right? We've changed our difficult integral into an easy integral. I'm not going to finish this question. I'll leave it for you to do. Finish this off. Check that I haven't made any mistakes in the rest. Check that the answer is equal to 2. So let me recap. To do a substitution in a double integral, we need to do two things. We need to calculate the Jacobian, and then we write dx dy is equal to the absolute value of the Jacobian du dv. Now, the reason I like this notation instead of using the letter J is because we have du dv divided by du dv, and we're left with dxy on the top is equal to dx dy. And that's easy for me to remember. That's easy for me to remember that I haven't used the wrong Jacobian. I haven't done things the wrong way around. And step 2, we also need to change the limits of integration. It doesn't matter which one of these steps we do first and which ones we do second. In the last example, first I did the limits of integration, and then after that I did the Jacobian, but it doesn't matter. Another one, calculate the integral from 0 to 1, integral from 0 to 1 minus x, square root of x plus 1, y minus 2x squared, dy dx. First, we need to choose a u and a v. And there's two functions here. There's an x plus y in green, and there's a y minus 2x in orange. Let's choose these. I'm going to choose u is equal to x plus y, and I'm going to choose v is equal to y minus 2x. And then I'm going to rearrange these to solve for x and y. X is u over 3 minus v over 3, and y is equal to 2u over 3 plus v over 3. You can check those later. I need the Jacobian of this coordinate transformation. So I do dx du, so dy dv minus dx dv dy du. 1/3, minus a third, 2/3. And that is equal to 1/3. So that's one of it done. That's the Jacobian done. The other thing we need to do is we need to change the limits of integration. Okay, important information is in the top, in the yellow box at the top. I have an xy plane and I have a uv plane. First of all, x is between 0 and 1. So I'm interested in the line x is 0 and the line x is 1. I also have that y is between 0 and 1 minus x. So that's two more lines that I'm interested in. I'm interested in y is 0 and y is equal to 1 minus x. The region of integration that we're starting with is this triangle. And now we can see, actually, we don't need one of these. We don't need x is equal to 1. They're a triangle. Triangle has 3 sides, so we just need these 3 equations. These 3 we need to change into terms of u and v. The first one, x is equal to 0. That means 0 is equal to u over 3 minus v over 3, which implies that u is equal to v. Next, y equal to 0. That means 0 is 2u over 3 plus v over 3, which implies that v is equal to minus 2u. And then there's one more still to do. We still need to do y is equal to 1 minus x. That's 2u over 3 plus v over 3 is equal to 1 minus u over 3 plus v over 3. Cancel this with this, move this over here. We just have u is equal to 1. So our new region, our region G, is going to be this orange triangle. We need the limits of integration here, and you know how to do that now. u is between 0 and 1, v is between minus 2u and u. Okay, so now let's go. Again, important information is in the yellow box at the top. We now have all the information we need to calculate this integral. We're going to do our substitution. Our new limits of integration are u between 0 and 1, v between minus 2u and u. Instead of square root of x plus y, I have square root of u. Instead of y minus 2x squared, I have v squared. And instead of dy dx, I have the absolute value of the Jacobian. Absolute value of a third is just a third, dv du. And again, because I'm lazy or because I don't want to use time doing this, I leave this for you to calculate. You can check that this is 2 over 9. An example from the book, we pick out the important points. Evaluate the integral from 1 to 2, integral from 1 over y to y, square root of y over x, e to the power square root of xy dx dy. We need to choose a u and a v. It makes sense that we choose one of them to be square root of xy and we choose the other one to be the square root of y of x. It doesn't matter which way around we choose them. Rearrange these and we get equations for x and y. X is u over v and y is equal to uv. We can change our domain R into a new domain of integration G. I'll skip that. You can come back and read this at a later time. And we need to calculate the Jacobian of this coordinate transformation. The book in this sometimes likes to use the notation J. And it finds that the Jacobian is 2u over v. So then we're ready to go. Do our transformation, integrating the double integral over g, v, e to the power u, absolute value of the Jacobian, 2u over v, du dv. We jump ahead, and you can read this in the book. I'm not going to spend time on it. And just convince yourself that the correct answer is 2e, e minus 2. In the last 5 or 10 minutes, I want to talk about substitutions in triple integrals. The idea is the same. We want to change our variables x, y, and z into new variables, and we can use the letters u, v, and w if we wish. What do we need to change? We need to change the domain of integration, and we need to change dx, dy, dz into absolute value of the Jacobian, du, dv, dw. Where the Jacobian is the determinant of a 3 by 3 matrix. So for example, if I wanted to convert Cartesian coordinates into cylindrical coordinates, remember the coordinate change was x is r cos theta, y is r sin theta, and z is equal to z. If you understand determinants, you can check that this is equal to r. And that's exactly what we were using before. Remember, dx, dy, dz is equal to r, dr, d theta, dz. What about if we're converting Cartesian into spherical coordinates? Again, we can do the same thing, calculate the Jacobian, calculate the determinant of this 3×3 matrix, and look what we get. If you understand determinants, you can check this. We get rho squared sine phi. Let's do one final example. This is the final example in today's lesson. Evaluate this triple integral by applying this coordinate transformation and then integrating over an appropriate region in the UVW space. First, we show you the pictures. We're going to be converting the green region D, that's the one we're starting with, into a new region G. I'm not going through all the details here. You can read this in the book. We convert the equation we're started with into new ones. We start with x is equal to y over 2, and we convert that into u equal to 0. We can convert x is y over 2 plus 1 into u is equal to 1, and so on. That tells us the new limits of integration. We also need the Jacobian of the transformation. Again, if you understand determinants of 3×3 matrices, you can understand that this is equal to 6. And then we have everything that we need. To finish this answer, we do our integral. So let me just repeat. We change the limits of integration to the new ones. And we change dx, dy, dz into 6 du, dv, dw. And after that, we do the calculation. You can check that we get 12. And that's the end of today's lesson. That's the end of section 14. That's the end of the topics which will appear on your next midterm exam. Next week, we're going to start talking about sequences, section 9.1, although I'm going to give more details than the textbook has about sequences. Are there any questions?